For deuterium molecule, I value equal to 1. Therefore, deuterium nucleus is a boson. I value integer means boson. So, when deuterium molecule, okay, diatomic molecule, this is one nucleus, this is another nucleus. I have told you already, I am just showing you only the nuclear geometry, not the electronic arrangement. Okay. So, when molecule undergo rotation, what will happen? The two nuclei exchange their position. I value for this nucleus is 1, it is a boson. This is also 1 because both the nuclei are one and the same. Okay, they are identical nuclei. So, the bosons are identical bosons. When the molecule undergo rotation, identical bosons exchange their position, which means the total wave function, right, must be anti-symmetric. I am very sorry. Wave function must be symmetric. Okay, as per Pauli principle, when two identical bosons exchange their position, then the total wave function must be symmetric. Total wave function symmetric means here there are two possibilities. What are the two possibilities? Number one, you know very well, total wave function is nothing but psi j into psi nuclear spin, correct? If j, the rotational state wave function, if it is symmetric, then nuclear spin must also be symmetric. Why? Then only symmetric into symmetric will give symmetric.
Symmetric.
Yeah. And what is the other possibility? If rotational state wave function is antisymmetric, yes, nuclear spin should also be antisymmetric. So that antisymmetric into antisymmetric is symmetric. Okay, so for total wave function to be symmetric, these are the two possibilities. Okay, now, the ground electronic state of deuterium molecule, okay, the ground electronic state of deuterium molecule is singlet sigma Gerard plus. Singlet sigma Gerard plus. This is the ground electronic state of deuterium molecule. I have told you, if the molecule belongs to singlet Gerard plus, then the states having even J values, J 0, 2, 4, 6, etc. These states, for that the wave function is symmetric. And states having odd J values, 1, 3, 5, etc. For this, the rotational state wave function is anti-symmetric. Okay, this you know very well. Keep this in mind. Now, observe carefully. I value is 1. Therefore, how many nuclear spin states are possible? I value is 1. I have given this formula already. Total, yes. Total number of spin states.
Sir.
Total number of spin states, what is the formula? 2i plus 1 the whole square.
2i plus 1 whole square.
Yeah, so 2 into I value is 1 here, plus 1 the whole square. So 2 into 1 is 2, 2 plus 1 is 3, 3 square is 9. So there are 9 spin states possible. Out of 9, how many are symmetric and how many are antisymmetric? Number of symmetric nuclear spin state. I write simply NS. Number of symmetric nuclear spin state is equal to, to find this, we can use this formula, correct?
2i plus 1.
Very good. I plus 1 into 2i plus 1. Put I equal to 1. So 1 plus 1, 2.
6.
Here 2 into 1 plus 1, 3. 3 into 2. Okay, we'll get the answer as 6. So out of 9, 6 states are symmetric nuclear spin states. Okay, and number of anti-symmetric spin states. Anti-symmetric nuclear spin states equal to, see, total is 9,
3.
6 are symmetric, so the remaining 3 are anti-symmetric. Okay, and remember, symmetric J states combine with the symmetric nuclear spin. Anti-symmetric J states combined with the antisymmetric nuclear spin states. Okay, so this is the idea. Keep this in mind. Now I'll show you how the spectrum, how the intensity variation are. Is there any line missing? Okay, we'll discuss. Listen. Before the nuclear spin affects the spectrum, okay, if you consider only the J levels, right? See, J equal to 0 level, right? It is symmetric. J equal to 1 level. J equal to 1 level has 3 rotational states. These are all antisymmetric states. J1. J equal to 2 level. It's an even level. J equal to 2 is even, so there are 5 states. These are all symmetric. Similarly, J equal to 3 is odd. So 1, 2, 3, 4, 5, 6, 7, and these are all antisymmetric states. So like that we have different levels. Now, in the presence of nuclear spin, okay, so what is the effect of nuclear spin? I wrote simply NS. NS means nuclear spin. Okay, I have written simply NS here, meaning nuclear spin. So what is the effect of nuclear spin? Listen, these are all rotational states. Okay, to this I am going to combine the nuclear spin states. Right? Now listen, because of this, what will happen? The total degeneracy get changed. And you know very well, symmetric will combine with the symmetric. Antisymmetric will combine with the antisymmetric, because I have given this formula already. Symmetric will combine with the symmetric. Antisymmetric will combine with the antisymmetric. Now, listen. Symmetric J is 1 for J equal to 0 level. See, J equal to 0 level has 1 symmetric state. And how many symmetric nuclear spin states are there? Out of 9, 6 are symmetric and 3 are antisymmetric. Correct? So, symmetric will combine with the symmetric. So, I have 1 here. 1 into 6. Yes, I'll get 6. 1, 2, 3, 4, 5, 6. So, we get 6 states. Why we get 6 states? Because J state is 1 and nuclear spin state, symmetric nuclear spin state is 6. So, 6 into 1 is 6. So, this is J equal to 0 level. Now, J equal to 0 level has these many states. Now, let me go to J equal to 1 level. In J equal to 1 level, it is an antisymmetric state. Okay, I have 3 here. And here antisymmetric state, antisymmetric nuclear spin states are 3. So 3 into 3, I'll get 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 states are there. 9 states. Why 9 states? 3 rotational states into 3 nuclear spin states. So I'll get 9. Then, if you go to J equal to 2 level, in J equal to 2 level, yes, here I have 5 states. All are symmetric. Symmetric will combine with the symmetric nuclear spin. Nuclear spin I have 6 here.
30 states.
So 5 into 6 I'll get 30. Let me write shortly like this: 1, 2, 3, 4, 5, 6, etc. up to 30 states. How I get 30? 5 into 6 I'll get 30 states. Similarly, if you go to J equal to 3 level, J equal to 3 is antisymmetric. Here I have 7. Antisymmetric nuclear spin is 3. So 7 into 3 I'll get 21. 1, 2, 3, 4, etc. etc. So I get 21 states here. How I get 21? 7 into 3. Like that I have different levels with different degeneracies. Now observe carefully. Here I have 6 states. 6 states, listen, as the number of states increases, population will increase. So I have some population here. But here I have 9 states. So population is more. Here I have 30 states. Population is very high. Here I have 21 states. See, compared to this level population is less. So, if transition takes place from 0 to 2, I have 6 states here, some intensity I will get. If transition takes place from J equal to 1 to J equal to 3, here I have 9 states, so intensity will be little high. Okay. So, the intensity pattern will be like this, isn't it? This is the Rayleigh. I am just showing you the Stokes line. Okay, whatever we discuss for Stokes line, the same thing is applicable for anti-Stokes. So I am going to show you only Stokes here. So first line j equal to 0 to 2 will appear with some intensity, j equal to 0 to 2 transition. Then j equal to 1 to 3 transition will appear little higher intensity because 9 states are there, 1 to 3. Then 2 to 4, observe carefully, 2 to 4, here I have 30 states. So 2 to 4 transition will appear with a very high intensity, 2 to 4. Then 3 to, after 2 to 4, 3 to 5. 3 to 5, I have only 21 states. Compared to this is less. So 3 to 5 intensity is somewhat less. Then if you take 4 to 6, 4 to 7, 4 to 6. 4 to 6 will appear with high intensity, 4 to 6. Then 5 to 7 appear with lesser intensity. So if you see the lines, listen, after the first line, then second line is less intense, third line is more intense. Less intense, more intense, less intense, more intense. So we get alternation in intensity, okay, in the Stokes lines as well as in the anti-Stokes lines. Okay, so even for deuterium molecule we get this alternation in intensity, right? Take note. Is this point clear to all? So we get variation in intensity in the case of deuterium molecule, right? Same thing is observed, right, in the case of nitrogen molecule. Okay, I'll just leave this as an exercise to you. You try to do that. Okay. See, third one. In the case of nitrogen molecule, where nitrogen atom mass number is 14. For N14, I value is 1. For N14, I value is 1. So we get similar observation as like deuterium molecule. We get alternation in intensity. Okay, so I'll just leave this as an exercise to you. Just try. Now, let me move on to the next example. That is third one. Regarding oxygen molecule, O2 molecule. This is very, very important. Take note. Oxygen molecule. Rotational Raman spectrum of oxygen molecule. How it will appear. Okay, we'll discuss. Rotational Raman spectrum of oxygen molecule. Listen. In the case of oxygen atom, that is oxygen atom having atomic number 6, mass number 16. Atomic number 8, mass number 16. In the case of oxygen molecule, okay, the nucleus of oxygen for which I is equal to 0. I equal to 0 means the nucleus is not spinning. I equal to 0 also corresponds to boson. It's a boson. Okay, as per the definition, I equal to 0 is also boson. So in oxygen molecule, we have two nuclei. Both the nuclei are bosons. They are identical bosons. Okay, so in oxygen molecule, we have two nuclei. For both the nuclei, I value is 0. I value 0 and they are identical. When the molecule undergo rotation, identical bosons exchange their position. Therefore, total wave function must be
symmetric.
Yes, symmetric. Total wave function must be symmetric. Okay, so this is the first point you should keep in mind. If total wave function is symmetric, you know very well there are two possibilities. Okay, psi j, if it is symmetric, psi nuclear spin should also be symmetric. Psi j, if it is antisymmetric, right, then psi nuclear spin should also be antisymmetric. Okay, there are two possibilities, right? This is 1, this is 2. There are two possibilities. Now observe carefully, this is very, very, very important. What is that? Ground electronic state of O2 belongs to triplet sigma Gerard minus state. Observe carefully. Ground electronic state of O2 belongs to triplet sigma Gerard minus. I have told you, listen, translational wave function is symmetric during rotation. Electronic wave function is symmetric during rotation. Vibrational wave function also symmetric during rotation. But the rotational wave function, right? Rotational wave function, the wave functions of the rotational states, it depends upon the electronic state in which the molecule belongs. Okay? So, if the electronic state is Gerard minus, sigma Gerard minus, then observe carefully, then J equal to even J values 0, 2, 4, etc. These corresponds to, for this psi J corresponds to anti-symmetric states. And J equal to odd numbers 1, 3, 5. For these states, psi J corresponds to symmetric. So psi J is, these rotational states are symmetric and these rotational states are antisymmetric. It is just ulta. Okay, it's just exactly opposite to sigma Gerard plus. So far we discussed 3 molecules. All those 3 molecules belongs to sigma Gerard plus state. Whereas O2 molecule belongs to sigma Gerard minus state. For this, even numbers are antisymmetric, odd number states are symmetric states. Okay, keep this in mind, very, very important. Now, we'll calculate how many nuclear spin states are there. Yes, total number of nuclear spin states. Total number of nuclear spin states. Yes, how many spin states are there for oxygen molecule? It is a homodiatomic molecule. 2i plus 1 the whole square is the formula. 2 into I value is 0 in this case. 2i plus 1 the whole square. Yes, 2 into 0 is 0. 0 plus 1 is 1. 1 square is 1. We have only one nuclear spin state. Now we need to find out whether this spin state is symmetric or antisymmetric. So use the formula. Number of symmetric nuclear spin states. Number of symmetric nuclear spin states. What is the formula? I plus 1 into 2i plus 1. Use this formula as a shortcut. I value is 0 equal to 1. What does it indicate? Listen.
Only one symmetrical spin state.
Yes, that's all. We have totally one state and that state is nothing but a symmetric spin state. So there is no anti-symmetric spin state here. Okay, so number of anti-symmetric spin states, let me write here. Number of anti-symmetric nuclear spin states. I am using some abbreviations here, so observe carefully. Number of anti-symmetric nuclear spin states equal to 0. So there is no anti-symmetric spin state at all. Right? Now, listen carefully. Before the effect of nuclear spin, how the levels are there, we'll discuss that first. See, this is J equal to 0 level, 1, 2, 3, 4, right? Energy increasing in this way. J equal to 0 level has only one state. Okay. J equal to 1 level has 3 states. J equal to 2 level has 5 states. 1, 2, 3, 4, 5. J equal to 3 has 7 states. 1, 2, 3, 4, 5, 6, 7. J equal to 4. 2 into 4 plus 1, 9 states. 1, 2, 3, 4, 5, 6, 7, 8, 9 states. Observe carefully. Oxygen molecule ground state belong to triplet sigma Gerard minus. In this case, even J states are antisymmetric.
Antisymmetric.
Odd J states are symmetric. So this is antisymmetric, this is symmetric. This is antisymmetric, the next one is symmetric. Okay, now I'll show you what is the effect of nuclear spin. Effect of nuclear spin. Right, but listen carefully, since it's the boson, the two nuclei are boson, so symmetric will combine with symmetric. Symmetric rotational state combined with the symmetric nuclear spin. Okay, now can anyone tell me, see this is rotational state, the ground rotational state is antisymmetric. How many antisymmetric nuclear spin states are there?
No, sir. No
So
state.
here I have one rotational state, but 0 antisymmetric state. 1 into 0?
0, sir. No.
0. So there is no state here. I just put a dotted line. Okay? J equal to 0 level has no state at all. Right? Then what about J equal to 1 level? For J equal to 1, this is symmetric. Symmetric will combine with symmetric. Yes, I have 3 here. 3 symmetric rotational state into 1 symmetric nuclear spin state. 1 into 3, yes, I'll get 3 states. J equal to 1 level has 3 states. Then J equal to 2. J equal to, this is antisymmetric. Nuclear spin must be antisymmetric nuclear spin states is 0. So here I have 5. 5 into 0 is 0. So there is no states available in J equal to 2 level. Similarly, if you go to J equal to 3 level, see, J equal to 3 level, I have 7 states here. So 7 into 1 symmetric. So 7 into 1 is 7. 1, 2, 3, 4, 5, 6, 7. Okay, this is how it goes. Okay, now listen carefully. Since there is no states available here, okay, there is no molecules. Then, can this transition occur? Can anyone tell me? Is this transition appear in the spectrum?
No, sir.
No.
Missing up line.
Yes. This line, this rotational transition does not appear. So, that line is missing. Whereas 1 to 3 will appear because in a J equal to 1 level, I have some states. I have some states here. So, I will get a line. For J equal to 2 level, again, see, there is no states. So, this line, there is 2 to 4 line. This line does not appear. So, this line does not appear. This line does not appear. Okay. So, alternate lines, okay, are missing in the spectrum. So, if you take the rotational Raman spectrum of O2 molecule, intensity, and this is scattered frequency, say this is the Rayleigh line. First line does not appear. See, this is Rayleigh. I'll write Rayleigh. First line, that is line corresponds to 0 to 2, does not appear. Then the next line will appear. 1 to 3 will appear. What about 2 to 4? 2 to 4 does not appear. 2 to 4 does not appear. Whereas 3 to 5 will appear. Right? Same thing happens in the anti-Stokes line also. Observe carefully whatever I have written here. Right? All those things are applicable for anti-Stokes. Okay, just for time consumption, right? I'm saving, just for saving time, I'm not writing those here. But keep this in mind. Whatever we discuss for Stokes, same thing is applicable for anti-Stokes. Okay, take it. Is this clear to all? Is this point clear? Yes, take it. Now tell me. Okay, just copy down this. Now, what will happen here? Let's write this.
Sir,
Yes.
the second page on இதுக்கு முன்னாடி பேஜ் சார். ஓகே சார்.
Right. Now, listen carefully. See, first I'll take a normal Homo diatomic molecule. Observe carefully. Suppose if you take molecule like hydrogen molecule, right, or deuterium molecule, or nitrogen molecule, right. See, in these cases, we get all the lines. Intensity variation will be there, but we get all the lines. Okay. In these cases, see how the rotational Raman spectrum will appear. The rotational Raman spectrum. So this is the Rayleigh line. This is Rayleigh. I will get first Stokes line corresponds to 0 to 2, and first anti-Stokes line corresponds to 2 to 0 or 0 to 2, whatever it is. Okay, first anti-Stokes line. The next line, 1 to 3 line will appear here and 3 to 1 line will appear here. Then next line, 2 to 4, 2 to 4, then we get lines like that. Okay, some variation in this. I'm not interested on variation in intensity now. Okay, I'm focusing on something else. Now observe carefully. You know very well the gap between adjacent anti-Stokes lines or adjacent Stokes lines is equal to 4b, correct? These are all normal molecule. The gap between adjacent Stokes line or adjacent anti-Stokes line is 4b, right? And the gap between Rayleigh line and the first Stokes line is actually 6b. Similarly, the gap between the Rayleigh line and the first anti-Stokes line, this is also 6b. Okay. Now, try to answer these questions. Question number 1. What is the gap between first Stokes and first anti-Stokes lines? Anyone?
Please.
12b, right? 12b, correct? 12b. This is normal molecule. All the lines are appearing. I am getting like this. Number 2. What is the gap between adjacent Stokes? Adjacent Stokes lines are adjacent
4B.
anti-Stokes lines. Yes?
4B, sir.
4b, correct? 4b. Now, listen, experimentally I can find the distance between the first Stoke and first anti-Stoke, and I can measure the distance between adjacent Stokes. Okay, tell me what is the ratio of the first Stoke and first anti-Stoke to the gap between adjacent Stoke and adjacent anti-Stoke. Okay, this is 12b divided by 4b, correct? So what is the ratio?
3:1.
3 by 1 or 3:1. If the ratio, listen, experimentally, after getting a spectrum, you calculate the gap between first Stoke and first anti-Stokes line, you will get some gap, and divide that gap divided by the gap between adjacent Stokes line. Divide it. If you get the ratio as 3 by 1, 3:1, then it indicates a normal Raman spectrum. No lines are missing. Okay. So in this case, see, this indicates that no lines are missing. If the ratio is 3 by 1, no lines are missing. Is this clear to all? Experimentally, you can check. Are you able to follow? Is this clear?
Sir, 3:1 வந்துட்டாலே no lines are missing, sir?
Yes, you're right.
For all molecules, sir? For any molecules?
Yes.
Okay, sir. Thank you, sir.
Right. Now, suppose if we take oxygen molecule, what will happen? See here. In the case of oxygen molecule, just now we discussed, listen, intensity, this is scattered frequency, and say this is the Rayleigh line. So, in the case of O2 molecule, first Stokes line does not appear, you know very well. 0 to 2 does not appear. Similarly, first anti-Stokes line does not appear. Second line, 1 to 3 line will appear. 1 to 3 will appear. Similarly here, 3 to 1 will appear. Next line does not appear. That is 2 to 4. 2 to 4 does not appear. This side I can say 4 to 2 does not appear. Right? That next line will appear. What's that? 3 to 5 will appear. Yes, here also 5 to 3 will appear. Are you able to follow this? This is how, see, even J level, see, lines starting from even J, 0, 2, lines starting from even J, those lines are missing. Right? Even J lines are missing. Right? Listen, if even j lines are missing, can anyone tell me what is the gap between the first line and the first line of here? Because there is no line here, right? There is no lines here. First line is this and first line is this. Can you tell me what's the gap?
20 B, sir.
Gap between first stroke lines. Okay. If you see the spectrum, I cannot say, right, whether it is 0 to 2 or 1 to 3 and all. Okay. I am getting some lines in the stroke side. I am getting lines in the anti-stroke side. What I am doing, I am just measuring the distance between the first stroke and first anti-stroke. Gap between first stroke and first anti-stroke. Okay. Anti-stroke is equal to, if it is O2 molecule, the gap should be, listen, this is supposed to be 6B and this is supposed to be 4B. Now this is 10B and this is also 10B. It should be equal to 20B. Am I right? Is this clear to all? Suppose if this line appears here, this gap is 6B and the gap between adjacent line is 4B. So 6B plus 4B is 10B this side and 10B this side. So totally 20B, correct? Is this correct? Hello? Hello? Are you able to follow?
Yes, sir.
Then, what is the gap between adjacent line? Adjacent
4B,
lines.
sir.
Strokes as well as anti-strokes. Yes. What is the gap between adjacent line? Gap between adjacent line.
8B, yes, sir.
8B, yes.
8B.
Since this line is missing, this is 4B, this is 4B. Since this line is missing, total the gap between adjacent line is 8B. Right? Now tell me what is the ratio? Ratio of this and this. This is 20B.
5:2.
This is 8B. Okay. Yeah. 10 by 4 or 5 by 2, correct? If the ratio is 5 by 2, what does it indicate? We measure the gap between the first stroke and first anti-stroke. Divide that value by the gap between adjacent line. If I get the ratio as 5 by 2, what does it indicate? It indicates that, which lines are missing? Even J lines are missing. Correct?
Even J line.
Even J lines are missing. Take note. This is very important. Okay, if the ratio is 5 by 2, it indicates that even J lines are missing, right, in the spectrum. Okay, so for oxygen molecule, keep this in mind. Very, very important question. For oxygen molecule, gap between first stroke and first anti-stroke is 20B. Often, in many competitive examination, people are asking this question. Gap between adjacent lines in strokes or anti-strokes is equal to 8B in the case of O2 molecule. Right? Clear?
இது only for oxygen molecule மட்டுமா சார் 5/2?
இல்ல மேடம், அப்படி இல்ல. ஈவன் ஜே லைன்ஸ் மிஸ் ஆகுற எல்லா மாலிகுலும் இப்படி வரும்.
எல்லா மாலிகுல்.
சரிங்களா? நான் இப்போ கொடுத்துக்க O2 மாலிகுல் எக்ஸாம்பிள் கொடுத்துருக்கேன். இது நிறைய மாலிகுல்ஸ் நீங்க புக்ல பாருங்க.
ஓகே சார்.
இருக்கு, மாலிகுல்ஸ் இருக்கு. யா, எந்த மாலிகுல் கொடுத்தாலும் ப்ரொசீஜர் தான். இந்த மெத்தடை நீங்க ஃபாலோ பண்ணுங்க. நமக்கு தேவை ஐ வேல்யூ தெரியணும். Now let me ask you a question. Suppose I have some molecule in which odd J lines are missing. How the spectrum, or how will you identify whether odd lines are missing or not? Odd J lines. Okay, I have some line, some molecule where odd J lines are missing. Okay, intensity, scattered frequency. This is Rayleigh. Okay, now first line appears 0 to 2. Even J, see, line starts from even J, that line appear. But line starts from odd J, 1 to 3, it does not appear. Similarly, line starts from even J, 2 to 4 will appear. Okay, line starts from odd J, 3 to 5, I'm sorry, dotted line. Okay, this dotted line. 3 to 5, this does not appear. Okay, similarly this side. See, line starts from 2 to 0, even j appears. Line starts from 3 to 1 does not appear. Line starts from 4 to 2 will appear. Line starts from 5 to 3 does not appear. Okay, now tell me what is the gap between first stroke and first anti-stroke?
12B, sir.
First strokes and first anti-strokes equal to, right? This is 12B. What is the gap between adjacent line?
8B, sir.
Gap between adjacent line is 8B. Then what is the ratio? 12B by 8B.
3 is to 3 by 2.
3 by 2. 3 by 2.
2.
If the value is 3 by 2, what does it indicate?
Add J lines are missing.
That's all. This indicates that odd J lines are missing. Odd J lines are missing. Okay. Odd J lines are missing. Is this clear to all? You able to follow?
Yes, sir.
Okay, no doubt. These are some important aspects required for CSIR exam preparation. Okay. Now we'll move on to vibrational Raman spectrum. First, I'll discuss vibrational, pure vibration. Assuming vibration is pure. Okay, pure vibration. Vibrational Raman spectrum. It is an assumption. You know very well vibration does not occur independently. Okay, so let us assume, right, what happens if vibration spectrum is recorded. Pure vibration is recorded. Observe carefully. You know very well energy, vibration energy formula is, what is the formula for energy? Vibration energy GV equal to V plus half into omega E bar minus V plus half the whole square into XC into omega E bar. Okay, assuming the molecule is anharmonic oscillator or Morse oscillator, this is the energy formula. V is vibrational quantum number, omega E bar is equilibrium vibrational frequency, and Xe is unharmonicity constant. All these things you know very well. This is the energy formula. I have given energy in centimeter inverse in wave number unit. Okay, this is the energy formula. Now, what is the selection rule? Selection rule. And you know very well selection rule always has two. One is gross selection rule, the other one is specific selection rule. In the case of vibrational transition, listen, polarizability of the molecule should change. Alpha should change during the vibration. During vibration, right? Polarizability of the molecule should change. Alpha should change during vibration. Right? This is called gross selection rule. And what is the specific selection rule? Delta V, change in vibrational quantum number, should be plus or minus 1, plus or minus 2, plus or minus 3, etc. Plus or minus 1 corresponds to fundamental vibrational transition. This is first overtone, second overtone, right? Yeah. Listen, these are all usually appear with very small intensity. In the case of Raman spectrum, it is even very, very small. So, we are not focusing on that. We are going to focus mainly on the fundamental vibrational transition. Okay. Now, what is the energy required for fundamental delta G for 0 to 1 transition. What is 0 to 1? V equal to 0 to V equal to 1 transition, for which delta V is plus 1.
Fundamental.
It is called fundamental vibrational transition. So what is the energy required for fundamental vibrational transition? Which is equal to, you know very well, omega E bar into 1 minus 2xc. I have written directly because we already discussed this. Right? This is the energy required for fundamental transition. Now, what is the frequency of the spectral line? Listen, frequency of the spectral line for Stokes line, frequency of the Stokes line equal to nu I bar incident frequency, and you know Stokes lines always appear in the lower frequency side. So minus, subtract this quantity omega E bar into 1 minus 2xc. Then frequency of the anti-Stokes line is equal to nu I bar plus omega E bar into 1 minus 2x. Okay, so we get a line in the lower frequency side and a line in the higher frequency side. Okay, listen, delta V0, I didn't write here, it corresponds to Rayleigh line. It corresponds to Rayleigh line. If delta V is 0, we get Rayleigh line. So frequency of the Rayleigh line is equal to incident frequency. Right? Now, if I plot this, how the spectrum is supposed to appear if pure vibration takes place, vibrational transition. In the case of pure vibrational transition. Right? And remember, here also I have taken diatomic from the problem. I didn't say that, it's very important. Right? This is applicable for this formula is applicable for diatomic molecule, right? And all these things are applicable for diatomic molecule. Now listen, if I plot intensity versus scattered frequency, right? Scattered frequency. So this is the Rayleigh line, right? Rayleigh line, and we get a line, right? Fundamental vibration transition line, Stokes line, and we get an anti-Stokes line here. Okay, Stokes line and anti-Stokes line, right? This Stokes line corresponds to 0 to 1 transition, and this Stokes line, anti-Stokes line corresponds to 1 to 0 transition. Whatever it is. Listen, it starts from ground vibration state. Population in the ground vibration state is so high, that's why the intensity is high. Whereas this starts from V equal to 1 level, population in the V equal to 1 level is comparatively less. At room temperature, even at room temperature, the population V equal to 1 is extremely small, so the intensity of this line is small. Remember, in the case of vibration spectrum, Stokes lines appear with high intensity compared to anti-Stokes lines. Okay, take note. Listen. This is actually schematic picture, but how the original spectrum appear? If you take vibrational Raman spectrum, in gas phase, these lines appear with many lines. Okay, they appear this line will appear as many bunch of lines, and this appear as many bunch of lines. Now we need to provide explanation for that. Okay, it means along with the vibrational transition, many rotational transition occurs. Okay, that's why we get bunch of lines. So next, I will give the heading like this. It is vibrational rotational Raman spectrum. Vibrational WIB, I will write shortly WIB. Rotational ROT, vibrational rotational Raman spectrum. Raman spectrum of diatomic molecules. Observe carefully. Diatomic molecules. Okay, vibrational rotational Raman spectrum of diatomic molecules. Now listen, I am going to use the same idea. So what is the energy? First point is energy. Energy is given by the symbol S. It depends on the vibrational quantum number and the rotational quantum number. What is the formula? V plus half into omega E bar minus V plus half the whole square into Xc into omega e. This is the vibrational energy formula. Plus rotational energy. I am assuming that there is no interaction between rotation and vibration. I have separated. See, vibration and rotation are not interacting. So in that case, we get the formula. We have to introduce the formula Bj into J plus 1. And in Raman spectrum, we normally do not consider the centrifugal distortion effect. Okay. So this is the energy formula in centimeter inverse wave. Now, what is the second step? Selection. Selection rule is this. Delta V, change in vibrational quantum number, should be 0, plus or minus 1, plus or minus 2, etc. Okay, observe carefully. Delta V0 corresponds to Rayleigh. This is for Rayleigh. Delta V plus 1 for fundamental vibrational transition, plus 2 for first overtone, plus 3 for second overtone. Anyway, in the case of Raman spectrum, overtone transitions appear with very poor intensity, so we do not consider normally. We focus mainly on fundamental transition. Okay. Then what about delta J? Delta J values. Yes. Delta J values can take delta J 0, plus or minus 2, plus or minus 1 also appear if the electronic state is non-singlet sigma state. Okay. If the electronic state is not singlet sigma, then delta J plus or minus 1 becomes allowed. Otherwise, delta J 0 and plus or minus 2 only allowed. Okay. Listen carefully. I have told you already, delta J minus 2, minus 1, 0, plus 1, plus 2. If delta J is minus 2, it is O branch. Minus 1 means P branch, Q branch, R branch, S branch. So in the case of vibrational rotational Raman spectrum, delta J minus 2, delta J plus 2 and delta J 0. Delta J 0 corresponds to Rayleigh. Minus 2 and plus 2 corresponds to O branch and S branch. O branch lines and S branch lines also appear. They appear. Whereas in the IR spectrum of diatomic molecule, we get P and R branch. You might be knowing that. P and R branch. But here I will get O and S branch lines for a vibrational transition. Right? Take it. This is a selection.
Sir, previous page warning for coming. Yes, sir.
Now, so I have given the selection rule. Now, listen carefully. Now I'll just show you the energy levels so that you can easily understand what I'm trying to say here. See? These are the rotational levels. Okay. This is J equal to 0 state level, J equal to 1, 2, 3, 4, etc. They are all rotational states, corresponds to ground vibrational state of the molecule. And we have rotational states 1, 2, 3, 4, 5, etc. J 0, 1, 2, 3, 4, etc. These are all rotational states, corresponds to V equal to 1 level. First excited vibration level. And remember, V0, V1, V2, V3, these are all corresponds to ground electronic states. So molecule is in the ground electronic state. But now we are going to focusing the transition between 0 to 1 called fundamental transition. And here I have what is called the virtual state. Virtual state. Okay. Virtual state appear only when light is exposed or when molecule is exposed to the light. Now what will happen? See, when molecule undergo transition from V equals 0 to V equal to 1. How the transition will occur? It will go from one of the rotation state of V equals 0 to the virtual state, and when it returns back, it stops at V equal to 1 level but ends with some rotational state. Okay. Now listen, I am not going to show you it goes to virtual and return back like that. I am going to show you directly the transition right from 0 to 1. Okay, so J0 to J0. This transition, see, J0 to J0. This is V equals 0 to V is the fundamental transition. During the fundamental transition, 0 to 0, right, is a Q branch line. It's a Q branch line. Then 1 to 1 is a Q branch line. Why? J1, here also J1, difference is 0, Q branch. This is also Q branch. So we get many Q branch. Okay, during a fundamental transition, many Q branch will appear. Right? Then this Q branch corresponds to delta J 0. Right? Then what about O branch and P branch? Delta J plus 2. See, 0 to 2. 0 to 2. It is final level is 2, initial level is 0. So 2 minus 0 is plus 2. Plus 2 means it is R branch. Right? This corresponds to R branch. These are all Q branch. These are all Q branch lines. And like that, many Q branch lines are there. I have shown only 3 here. R, the next R will be 1, 2, 3. Next R will be 2 to 4. Like that, these are all R branch lines. For which delta J equal to plus 2. Here delta J equal to 0. Right? Then we have lines from delta J minus 2 also. Right? How it will appear? Delta J minus 2. So 2 to 0. See this? 2 to 0. It starts from 2, goes to virtual state, return back to J equal 0. That's the meaning. 2 to 0, it corresponds to anti-Stokes line. I'm sorry, it corresponds to delta J. Final is 0, initial is 2. 0 minus 2 is minus 2. This all corresponds to R branch and this all corresponds to O branch. Right? Then 3 to 1. Then 4 to 2. Okay, these are all lines corresponds to O branch. Okay. So during the fundamental transition, we get Q branch, we get R branch, and we get O branch. Okay. Now I'll show you what is the energy required for these transitions and how the transition will appear in the spectrum. Okay. In all these transitions, see, molecule moves from V equal to 0 to V equal to 1. So it is a fundamental vibration transition. But during the fundamental vibration transition, many rotational transitions occur, and that's why we get bunch of lines. Now, we move on to the next page. So it's a very simple one. You can easily understand this. Now, listen carefully. What is the energy required for the transition? That is delta S. Delta S is equal to energy required for vibrational transition plus energy required for rotational transition delta S. Okay. What is the energy required for vibrational transition? Right? For fundamental, it is equal to omega E bar, omega E bar into 1 minus 2xe. Am I right? For fundamental.
Yes.
Yeah.
Yes, sir.
This is for fundamental vibrational transition. Plus, what is the energy required for the rotational transition? Okay. Isn't Bj into J plus 1 for higher level, right? In final state, right? Let me take this as J prime, higher rotational state, minus B J double prime into J double prime plus 1. These are all lower rotational states. This difference we should take. Okay. Now, is this clear to all? Or I can write directly omega E bar into 1 minus 2xe plus B into 4j plus 6. Am I right? Am I right? Do you remember this value formula? We discussed this in the beginning. If delta J is plus 2, then the energy required for the transition is this, right? Just check it. V into 4j plus 6. I wrote this formula. This formula is applicable for delta J plus 2 or minus 2. Okay, we get either plus or minus, depending upon the J prime and J double prime values. Okay,
J
now
plus
listen.
2 J difference sir.
Yes. Now observe carefully. What is the frequency of the spectral line? Frequency of the Stokes line. Observe carefully. Right? Frequency of the this is for delta J plus 2 and minus 2. Delta J plus 2 plus or minus 2, we get this. For delta J 0, this is 0. So we get just omega e bar into 1 minus 2x. For delta J 0. Okay, called the Q branch lines. Right? For Q branch lines, the two things are equal. Okay. Now listen carefully. So frequency of Stokes line. Let me write Stokes lines first. Let me give the heading like this: Stokes lines. Okay. Stokes lines appear in the lower frequency side. Right? So frequency of O branch line. O branch. Right? What is the frequency of O branch lines? And what is the frequency of Q branch line? And what is the frequency of S branch line? Stokes. Okay. For Q branch line, delta J is 0. So, for Q branch line, we get nu I bar minus omega E bar into 1 minus 2xe. This is fundamental vibrational transition, energy required, and this is the incident frequency. Subtract this, we will get the Q branch line. Okay, and listen, for all Q branch line, 0 to 0, 1 to 1, 2 to 2, right? For all the Q branch line, same energy is required. So you get single Q branch line. Observe carefully, we get a single Q branch line. We will get a single line. Now, we'll go back to the O branch. How the O branch lines will appear. Is this clear to all? Are you able to follow? If you are not able to follow, please tell me, I'll help you.
திரும்ப சொல்லுங்க சார் the difference எப்படின்னு.
Yeah. Listen. In the Stokes line, listen, this is the energy, this much energy is required for vibrational transition. If I subtract this from incident, I'll get Stokes. But depending upon the J, change in J, I'll get O branch, Q branch and S branch, right? So in the Stokes side, we get O branch, Q branch as well as S branch. So what is the O branch? First I'll write Q branch. What is the Q branch? Q branch means, listen, J prime, J double prime, both the values are same for Q branch. So if this is same, this is same. If you subtract, it will get 0. So this becomes 0. I'll get only this. So if I subtract this value from incident frequency, I'll get Q branch. But for all Q branch, we get the same energy, same frequency, right? So we'll get only one line for all the Q branch. What about the O branch? Okay, for O branch, you know very well, delta J should be minus 2. Delta J should be minus 2 for O branch. Right? If delta J is minus 2, right, what does it indicate? It indicates that we get lines at a little lower frequency compared to Q branch. What is meant by that? Is an incident minus omega E bar into 1 minus 2xe. This is for vibrational transition. From this, listen, to this you add plus V into 4j plus 6. Yes, this will give the O branch lines. O branch lines appear little higher frequency side of Q branch. Q branch, okay? Little higher frequency side of Q branch. What about S branch? For S branch, nu I bar minus omega E bar into 1 minus 2xc. This is for vibrational transition. O branch, S branch line will appear in the lower frequency side because delta J is plus 2. For S branch, delta J is plus 2, right? And you have to subtract. So minus B into 4j plus 6. Okay, take it.
சார் மைனஸ் பண்ணது எதனாலன்னு சொல்லுங்க சார்.
For S branch, delta J is plus 2, right? Delta J is plus 2. Okay. If you put delta J plus 2, what will I get? Any idea? We have discussed already. Just go through previous papers. We have already discussed what happens if delta J is plus 2, what happens if delta J is minus 2. Do you remember the values? Okay. If not, no problem. You just try with this formula. Put delta J minus 2 and delta J plus 2 and check it. Listen, see, I'll show you. I'll just show you, since you asked this question, listen. B J prime plus 1 minus B J double prime into J double prime plus 1. Correct? This is the formula. If delta J is minus 2, what is meant by that? Delta J minus 2 means it is O branch. Okay. O branch means, listen, delta J minus 2 O branch, meaning final level is less, initial is less, final initial level is high. So J prime should be less and J double prime should be greater. So J prime minus J double prime should be minus 2. Okay, this is final initial, sorry, the final and this is the initial.
Wait.
This final, this initial, right? J prime minus J double prime is minus 2. Okay, so if I substitute this here, J prime equal to, say, J single prime equal to, I'll get J double prime minus 2. If I substitute this here, I'll get B, take B as common, Wherever J prime is there, put this value. So I'll get J double prime minus 2. And if I put J double prime minus 2 here, minus 2 plus 1 is minus 1. And I have J double prime into J double prime plus 1. Okay, if you multiply this, what we get is J double prime square, then minus 2J minus 1J, I'll get minus 3J double prime plus 2. Here, J double prime square minus J double prime. So these two cancel. Minus 2J minus J. Observe carefully, this is very important. I'll get minus 4J double prime plus 2. Correct? Is this clear? Minus 4J double prime. Hello? Are you able to follow?
Yes, sir. Yes, sir.
So we get this formula. I have minus sign in front. If I take minus as common, okay, if I take minus as minus common, I get minus B into 4J double prime minus 2.
And J double prime is the
this
final
is for,
value.
Yeah, listen. So this is what we get. Listen, this is for rotational change. Listen, you know very well. For O branch line, Stokes, right? For Stokes O branch line, incident frequency. From this, you have to subtract the energy required for fundamental transition. That is omega e bar into 1 minus 2xe. Okay, omega e bar into 1 minus 2xe. This is the energy required for vibrational transition. Plus or minus this one. Okay, minus b into 4j double prime minus 2. Okay, this we have to subtract. Okay, if you multiply this by minus, then incident frequency minus omega e bar into 1 minus 2xe. This become minus or minus plus into b into 4j double prime minus 2. Is this clear? So we get plus sign here. Are you able to follow? Hello? Are you able to follow?
Yes, sir.
Right, so we get plus sign here. So that's why I wrote simply in this manner. For O branch, we get plus sign. For S branch, we get minus sign. See, I have written simply J. I didn't show that it is J double prime J sign. I wrote simply J. That's why I used that formula as such. Okay. For J plus 6. If you use J prime, J double prime symbol, you will get. You will never get J plus 6. You will get this one. This one. Okay. Don't worry about that. That's not important. Okay. For O branch, we get plus. For S branch, we should get minus. Right? Now listen how the spectrum look like. Then you can easily understand this.
Sir,
Yes.
single line எழுதிருக்கீங்களா? அதுல rotational lines கிடையாது. அதனால vibration மட்டும் இருக்குறதா single line.
Yes.
எப்படியே rotational வந்தாதான் நமக்கு வந்து பஞ்சா கிடைக்கும் lines அப்படிதானே சார்?
ஆமா. கரெக்ட். இங்க rotation நடக்கும், பட் rotation நடந்தாலும் delta J 0ன்றதுனால எனர்ஜி வராது, டிஃபரன்ஸ் வராது. எல்லா ரொட்டேஷனல் டிரான்சிஷனும் சேம் எனர்ஜி தேவைப்படும், அதனால அந்த லைன் அப்பியர் ஆகும். புரியுதுங்களா? Now listen how the spectrum will appear. Listen. See how the spectrum will appear. It's very, very important. Okay. Now I am just showing you vibrational, rotational, Raman spectrum of diatomic molecule. Okay, this is the Rayleigh. This is the Rayleigh line. Okay. Listen. First, the Stokes line, right? For fundamental vibration lines, Stokes line will appear on the left hand side, anti-Stokes line will appear on the right hand side. Right? This is nu I bar. Nu I bar minus omega e bar into 2xe. This is Q branch. For Q branch, we get only one line. O branch will appear in the higher frequency side of Q. So these are all O branch lines. Let me show you here. These are all O branch lines. Right? All these lines are O branch. They are appear in the higher frequency side of Q. And S branch will appear in the lower frequency side of Q. These are all S branch. Keep this point in mind. Okay. O branch, Q branch, S branch. Right? From left to right, if you move, S branch appear with the lower frequency, O branch will appear with the higher frequency. So for O branch, we should get plus sign here. Okay, that's why I told you. For O branch, okay, we should get plus sign here. It will appear in the higher frequency side of Q branch. See, this is Q. These two are same, right? Q branch. O branch will appear in the higher frequency side. And S branch will appear, see, this is Q minus of this. So, S branch will appear in the lower frequency side. This is how the spectrum will look like. Right? Then, this is for Stokes. Similarly, we get anti-Stokes. Anti-Stokes also, I'll get a Q. This is Q. And right hand side, I'll get many lines. These are all S branch. And we get many lines. These are all O branch. Listen, this is exactly reflection line. See? Here I have O in the higher frequency, S in the lower frequency. But in the anti-Stokes, O will appear in the lower frequency, S will appear in the higher frequency. It is exactly a mirror image of this. Okay, but you know very well, anti-Stokes lines appear with a lesser intensity. Okay, Stokes lines appear with a higher intensity. Okay. This is how the vibrational spectrum of vibration spectrum will appear. Right? Is this clear to all? புரியுதுங்களா?
சார் புரியுதுங்க சார்.
Yes.